did it before, and I don't think it will be useful now to give you full definition, but just assume that we have some processes that are solutions of some simple stochastic differential equations, and also you can think about as kind of diffusion without ellipticity, so hyperelliptic diffusion. So this is the case that I want to consider, and the question is about this set. So I look at all points that are visited by the process and then intersect it with some Borel set and see what we obtain. And typical question, we take some Hausdorff measure. I will, of course, define what kind of Hausdorff measures we will be considering, and then we try to estimate it somehow. So this is the question, and a little bit about why I asking this question. Well, it is interesting for me. It is interesting to study intersections or self-intersections of the processes, and in particular, I want to have a condition that such set is empty or non-empty with probability, with positive probability. Yeah. So. For example, when it is empty, I don't. What kind of condition can be here? So I have some results in this direction, but it is not even clear in which way it is better to write this condition. So I decided to study Hausdorff measures, maybe in attempt to better understand the structure of this. Intersections, so maybe I will also better understand what kind of conditions I need for the existence of intersections and self-intersections. And of course, I take independent processes for the exact reason that if we take one process and look at self-intersections of this process, then it often can be related to intersections of independent processes. So I just, for today, I just look at independent processes. And of course, here is V, if V is diagonal, X, 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 and we look exactly at intersections of independent processes. And if we take instead some more complicated set, then we can say that it is intersections of functions of these processes. Yes? So we can look at intersections of some kind of processes of this type. So this is the questions that I want to consider, and just a couple words about the result, what is known about Hausdorff measures of such sets. Well, I did not prepare a detailed explanation of known results, but from what I read, I think that this exact questions just wasn't considered for this type of hyperelliptic diffusions, and not just usually such type of questions, they're concerned about the range or even the range of one process, not range of multiple processes together. And intersecting with V only exists only in cases when V is diagonal and only for very specific processes. So I can name some names, for example, some works of Legal in these directions with different co-authors. Also, there was some works of Taylor, early works for range of processes for Hausdorff measures and dimensions of a range of different processes. Mostly Levy processes, I think. Maybe some Gaussian processes were studied as well. And later, there was some works of Hashnevi-san with different co-authors also in these directions. Yeah, so this is very short history of this question. And so, yeah, now I want to explain about a little bit more about this process, why I'm taking such process, and what do I need from the processes YK. So in fact, the only two things that I will be using today, I think, if I remember correctly, yeah, maybe I will need something else, but the two main things that I will need is, first of all, this is estimate for the for the potential, basically. So here we can also write integral to infinity of step minus lambda t and have the same estimate. But also I maybe don't need e power minus lambda t, because I consider processes. If you look here, I said that Q1 greater than 2, that means that the process is transient. So process is transient, and we do not need to think about other situations. And here also power will be always negative, so this is not a problem. Yeah, but it is important to know that this is the main reason why this type of processes can be investigated in this way, as I will show. Yeah, so this is the main inequality for me. And also there is an additional thing that it is useful to know. Basically, it follows in some way from the previous, but also from other properties of the process yk. We can conclude that the probability hitting a ball has this asymptotics if epsilon is small. So the only thing we have to make sure is that we are far away from the ball. So we're some distance away from the balls. And if we take small balls, then asymptotics will be like this of hitting this ball. Okay, so this is what I need from the process. Now, what do I want to do? I want to consider Hausdorff measures. So we have a general definition of Hausdorff measure on a metric space, and even more general, we can take, instead of HR, we can take any function that converges to 0 at 0 and positive, yes. So then it is standard definition. Federer and other sources exactly the same definition, have exactly the same definition. So all I need that maybe here should be Borel sets AOI, but it doesn't matter because I will need mostly the second definition, where in the second definition, the difference is that we use not any set of small diameter, but exactly balls, and also closed balls, although maybe it's not that important, but closed balls. So we will consider coverings of by closed balls of a set, and then we will compute some sum of HR from their radii, and then this sum has to be as small as possible over all coverings, and take epsilon to 0 and see what happens. This is well known. This is called spherical Hausdorff measure, probably, if I remember correctly. So, and also it is well known, or it is proved in the book of Federer, but also it is kind of trivial because we can cover the set of diameter rho by the ball of radius 2 diameter epsilon. We can cover this ball radius to epsilon, so it is trivial, this estimate, but nevertheless, we know that it is equivalent. Yeah. So if this is finite, then the spherical is finite, and vice versa. So this is so in the future I can work with just spherical for my purposes. So now I want to define a special Hausdorff measure, although as you will see, it is not too different from the previous slide, but still, instead of using balls, I use product of balls. And instead of using the same radius, I use different power of the same of the radius here. So radius here is different not only not in the sense that they are all different, but it has different proportions. So, for example, if we can have such situations that here a power is one power is 1, and the other power is 2. So we consider the product of two balls. One of these balls have radius epsilon, and the other one have radius epsilon square. So this will be what we have here then. And these powers are fixed, so they are fixed, and we will consider covering with such boxes, which are different sizes in different directions. So this is the idea. So I think I need for this type of situation when we have different processes potentially and different with different properties, I need to take not necessarily standard boxes, but some skewed boxes of this sort to and consider the corresponding spherical. It is can also maybe called spherical Hausdorff measure. In fact, it is equivalent to this spherical Hausdorff measure with some distance. We only need such distance so that we have this. Oh, I'm sorry. Here it has to be inclusion, of course, not inequality, but yeah. But the idea is that. We always can have such distance because we can always find this distance as sum of some powers of different distances from in different gk. So, for example, it can look like this. So sum by k. And we just need C large enough so that this will be a distance, and I think this should work for this. So it is maybe not that important, but yeah, we can relate this as type of Hausdorff measure with standard cylindrical in metric space, not cylindrical, spherical. Yeah. Okay, so this is the type of Hausdorff measure that I want to use to measure the random sets. And it is interesting. It is, I think, it's relevant that we can also define a capacity that is related to basically the same. The same construction. So we have suppose that instead of x power r, we have x power minus r here. So here is a negative power, and then we look at all measures that are have weight 1, total measure of x is 1, and they are concentrated on the set A. And then we look at such integral and take its supremum over x. And two situations are possible. The supremum is finite, and the supremum is infinite. So when the supremum is infinite, this is bad. We do not want that. So if at least one measure have finite, then we can define this, yes, and then we have capacity corresponding to this distance and to this set and to this function phi. And if no measures, no such measures have this supremum finite, then it is always infinite. So then capacity is declared to be 0. This is this is small set. We cannot have it is not big enough to have such good measures on it.
Alexei, let me ask you, capacity now is defined in such way, or what?
Yes, it is defined like this. It is a standard definition from the paper of Kamitani. Yes.
I think that when we have initial Newtonian capacity, we can use another definition, yes? And even related to the possibility of Brownian motion to visit the set, yes?
Yes, so it is of course all related, and yes, there is another definition. So here instead, if I use instead of this, we use this. This, yeah, you mean this. And if I use this, I can also define capacity. This will be a slightly different capacity. The problem for me with this that I did not find a good enough explanation in literature how this all related in a general enough case. So maybe I think I found it eventually, but I cannot explain it right now. So basically, you're right that this capacity and this Bezikovich Reed's capacity, maybe it's some
Yeah.
partial. Yeah, so it is they are related, and in fact, if we have RD with Euclidean metric, they're equal.
Mhm.
This is well known, but my question was if they are equal in my situation, and this I cannot answer right now, but I have hopes that they are actually also equal. So
Yes,
maybe.
but I also am asking about the relation with the Brownian motion. So we know that if we have set of positive capacity in 3 dimension, then it is visited by
Yes,
Brownian.
yes, of course. And this is capacity is also related to the visiting of sets. You're absolutely right. But for this, we need specific function phi. If for some specific function phi we have capacity 0, then the set is not visited and so on. So it is the
So
same capacity,
the
yes.
same happened in your situation too, yeah?
Yes, but also
Mhm.
if for me, I want to measure this for random sets. So
Mhm.
it is kind of both for the sets that I visit and the set that after the visits we have some sets that intersection with the trajectory. And for this we also can ask if the capacity is 0 or not
I
for
see.
with regard to some. So it is possible. For me, it is important that this capacity is related to the Hausdorff measure. For
Mhm.
example, Kamitani proves that if capacity is positive, then corresponding Hausdorff measure is infinity. And there is a reverse theorem, but I cannot formulate it because it is not general. Because for reverse theorem, there are additional assumptions. For example, we need to have Euclidean metric. And again, I am not sure that in my specific situation we have a reverse theorem, but I think I know where I can find it. So maybe it is true. I found the paper, but at the moment I cannot explain. But maybe also true. So I have also hope that this capacity and this capacity, they both related to Hausdorff measure in such a way. There is a
I see.
gap. Yeah.
I see. Thank you.
Yes. So, but there is a gap. When we go in the opposite direction, then maybe we need uh, to step a little bit to make this smaller, I think, or bigger. So if capacity. mm, Yeah, so if capacity if R is bigger, then we measure bigger sets. So we need maybe minus delta, so we can measure smaller sets is greater than 0. So something like that. Yeah. So this is. I hope that this is true, and I hope that it is known. But at the moment, I cannot. I cannot give you exact reference. So the idea introducing capacity is exactly so we can relate it with Hausdorff measure, and maybe in terms of capacity some things will be easier. So this is the idea. Okay, and of course I also need to relate. Yeah, and this is very interesting. This lemma explains why I need not one Hausdorff measure, but a whole family of Hausdorff measures. So remember that for uh, when I wrote condition for the existence of intersection of independent processes, and the condition looked well similar to this. So what do I mean? I mean that in the place of potential, I have this product. Here has to be xk, yk. So it is product of different coordinates, and here also xk, yk. I'm sorry. So this is a product of typically we have q from xy is equivalent to it is estimated by rho power x y power 2 minus q. This is the equality that I showed you. But we have not one process, but n processes, some number of processes. And for each process, we have each own potential. So here, actually, the correct way of dealing with intersections of intersection is to consider the product of such potentials. And then we look at this supremum, and if it's finite, then corresponding capacity is greater than 0, and the set is visible. If we correctly choose HK, we can say that the set is visible. And in fact, I have some papers with similar results. So this is the typical conditions that we need we usually have for the process to have intersections. And because of this is the conditions that we have to study. And it turns out that if we look at this previous slide, yes, so this is different. So here we have not many distances, but one distance. So we have to transfer to this situation if we want to use this theory. And it turns out that we can do it like this. We can use this inequality. Here is just Jensen inequality for logarithm. And then sum of Lk is 1. Yes, so this is Jensen inequality. And because of this, I have instead of this product, I have maximum of minus 1 power, maximum from some RK. So this is actually equivalent to this. It is not normally, it is not distance, but it can be distance, and it is equivalent to the distance that it is here. So in fact, we arrive in this exact situation. If we transfer from the capacities to Hausdorff measures, then Hausdorff measures that we obtain is exactly those that I defined here. So this is the reason that I need this set of Hausdorff measures, not one Hausdorff measure, but set of Hausdorff measures related to not one. In a sense, we have instead of dimension, Hausdorff dimension is when the Hausdorff measure transfers from infinity to 0, right? So it is the exact moment. So here, instead of having exact moment of transfer of 1, in one variable, we have many variables. So for example, in dimension 2, we can look at, instead of Hausdorff dimension, we have some kind of line. Yes, so here we have always, this is parameters are 1 or 2. So here we have always Hausdorff dimension plus infinity. Here we have 0. And then we transfer between them somehow like this. So this is the picture. So instead of describing the process with dimension, we describe it with such a kind of diagram. At least in theory, I think it's appropriate in this situation because of this lemma. So because of if we have this condition, then we have not one but a series of relations with Hausdorff measures. And the proof, of course, uses this theorem of Kamitani and this inequality. This is just trivial. Okay. And now, so now the first theorem that I want to prove. Just a second. Yeah. So what I want to do, so the first, what I want to do is I want to say something about the Hausdorff measure of this V intersect with trajectories. So, for example, I can do it like this. I can suppose that I have some Hausdorff measure of the initial set is finite. And the only condition that I need is this. Then, V has to be bounded and Y has to be some distance from V. So this is just a picture here. So we have some set and some point that some distance away. And then P, Y almost surely. So when we start from this point Y, then the process if we look at its intersection with the set V of all the trajectories of all processes, then we have its Hausdorff measure is finite with this specific parameters. Okay, so let me explain how I want to prove that. So the proof is as follows. We take some covering of the initial set V. So here you can assume that this the union of AI covers V. So this is some covering of set V, and then we can estimate the sum of epsilon I multiplied by this indicator. What does this mean? So we are counting not all of this AI, or we're counting those AI that intersect with the out trajectories. So this means that this condition is we select only those sets from the cover that actually cover the also V intersect Y 0, 1 over n. So given the covering of the set V, we obtain the covering of the set V intersect trajectories. And because of this, we can estimate this sum. This is a sum that corresponds to this covering in the definition of Hausdorff measure, and we can estimate it by taking expectation. If we take expectation, it turns out this indicator is just a probability of hitting the set each of the ball. Well, because of independence, we can write it as a product of probabilities, and each probability estimated by epsilon 1 power. Okay, so here I also have this power, but then it's at power 2 minus qk. Sorry, qk minus 2. Yeah. So this was the estimate that I showed you, and I for the heating probability, and I use it here and immediately obtain this estimate. So in this way, I estimate Hausdorff measure. In fact, because we then can just insert expectation inside, yeah, because just lemma for 2 and then just inside infinitum, and we obtain result. So we estimated, in fact, have this estimate for the probability for the expectation of the Hausdorff measure. If we have this finite, then of course we have this finite, and if this is 0, then also this is 0. But this is not important, I think. So this is the first theorem that allows me to say something about Hausdorff measure when the Hausdorff measure is finite under some condition. And so the next, what I want to do is I want to say that I want to give some conditions under which this Hausdorff measure will be infinite. So estimated in a different direction. This is unfortunately a little bit more complicated here, and for this I need an intersection local times. And because of this, I need to introduce random measure L on X. Here I do not prove that existence of such measure, but in fact, using results from my paper, I think it is possible. It is not any random measure. It is exactly intersection local time. In this particular situation that was considered in my paper. But for this to exist, I need some conditions. So instead of writing this condition, I just assume that it exists now, and then I think in this way I will save time, because there is no need to write this condition why this exists right now, and of course then this will be more general. So maybe there are other situations, maybe for other processes when we can define the similar object, and then it also works. So let us assume that it exists, and then we also need this relation So this is just that integral square of the integral is written in the following form using the density. It is just it is important that here we have some measure nu. Yeah, so here I said that it's just any measure, but in fact we have to when we define this intersection local times, and this measure can be found. It is some measure. It is, in fact, in my paper, I think it is equivalent to this surface measure on H. H is a smooth manifold, so we can have surface measure on it, and nu is equivalent to the surface measure. So this will be nu, and this equality is what we will have for intersection local time too. So using this, I will prove the following theorem. So here, unfortunately, I have to assume not just that some Hausdorff measure is finite, but this condition. So this condition, it can be viewed as condition for existence of intersection V and Y. So, but yeah, it is. Maybe it's not exactly equivalent to what I have now in my paper, but it is kind of part of the conditions that I need for this to be non-empty. But also it is the condition for the capacity to be positive, yeah, of the set. So this is actually I did not define the corresponding capacity, so I cannot say about capacity, but at least the supremum can be understood also as capacity, and it is known that such capacity also exists for such case from some works on multi-parameter Markov processes, but it is not important. So suppose that we have this condition, then additionally, I suppose that this intersection local time is actually intersection local time in some sense. So it catches intersections. Yeah, so it's positive. Otherwise, it doesn't make sense to be intersection local time. And then I have that some specific Hausdorff measure is infinite, almost surely. Well, you know, here I probably have to write with positive probability. I'm sorry. With positive probability, because in fact, it is possible to, with positive probability, it's possible to completely omit the set. Yeah, so with positive probability, I'm sorry, I think I changed it in a different spot, but here I forgot to do it. I'm sorry. Yeah, here, yeah, you see it's positive probability. Here I changed it and forgot to change it here. Sorry. So yeah, and this is the theorem. So this is what I want to prove. And the idea actually is from the paper of Legal on the hyperelliptic diffusions. There Legal explains how to find Hausdorff measure of the range of hyperelliptic diffusion. Turns out that the same works here, except I do not need a precise estimate. So I do not need to estimate here. In Legal, he estimated not just first, but p moment of this. But I do not need this because p moment is only needed if we have additional logarithmic term in the definition of Hausdorff measure. Since I do not have it, I do not need p power. I can just use first power. And the most important part is that here, if this density, yeah, if we integrate it over time, here time is not one-dimensional, just in case. This T1, T2 are multidimensional. There are n different times here and here. So here we have actually some big integrals that I decided not to show you all these integrals because it's actually the idea is just very simple. just take supremum over some variables and we obtain this estimate. It's just more or less. I don't think I need to explain it too much because also it's the same done in the paper of Legal basically. So it's just standard. Except, yeah, well, I have a slightly different case, but it still works. And then if we have this estimate, then we have this estimate. And yeah, here I just multiply add HK, subtract HK, and then estimate rho k power HK minus QK plus 2 as epsilon. So RK is less than equal than epsilon, and then because we are in this corresponding ball, and epsilon power 1 over RK actually. So yeah, so this is this multiplier, and what we only left with HK, and this is what I write here, and then we have this estimate. So this is the estimate for the first moment of this of the intersection local time from some small ball. What do I need it for? I need it to estimate to say that in fact the limit the upper limit of such intersection local time from the small ball divided by epsilon converges to 0. And it is true because, well, it is also kind of standard idea. It is basically Borelli-Conte lemma here. So we take some moments, some epsilon L, some sequence, and over this sequence, we can check that this holds only finite number of times because of this. And because of this, we have convergence over such epsilon L, and then convergence over all epsilons easily follows. So then we have this with probability 1, and almost surely, almost everywhere with respect to this L. And as a result, we can also obtain this. Here, I also skipped some computations, but in fact, it is, yeah, we just have to consider set on which this convergence is fast enough, and then on this set we will have estimate epsilon less than yeah. So we for example can use that this will be less than equal some constant epsilon. Yeah, and this actually compares measure of this set with corresponding Hausdorff dimension of the set, because if we sum these measures, we obtain measure of the set. Yeah, and if we sum this, we obtain estimate for Hausdorff measure because of definition of Hausdorff measure. And yeah, this compares Hausdorff measure. This is yeah, again, standard argument, and that is why it is not explained here in more details. And in this way, I prove that it is in fact greater than 0. Yeah, so I needed to say here that it is greater than 0. I'm sorry. Yeah. I proved one thing, but stated completely different. Sorry, but the idea is basically that if we prove it is greater than 0 at some point, then we can increase a little bit here, and then we also obtain plus infinity. So maybe it is also true with plus infinity. But yeah, I'm sorry. I should have stated as greater than 0. Yeah, and the idea is from this paper of this proof. So this is basically most of what I wanted to say. Unfortunately, yeah, it will be interesting to look at the examples and to find if there is some more precise relation between capacities and Hausdorff dimensions, as I showed you. But for now, it is all I have to say.
Okay, thank you very much for interesting talk. And maybe somebody have questions or comments, please. Actually, I have a question which is very related to the title of the paper which you showed at the last slide, but I formulated this question in the beginning for myself. In the initial papers of Taylor, we see that he related Hausdorff dimension of the set of self-intersection for planar Brownian motion to its trajectory properties, like module of continuity. We remember that in Levy law of about module of continuity of the Brownian motion on the interval, we have just one logarithm t multiply on the logarithm. Square root of t multiply on the logarithm. So Taylor related this to the capacity of to the Hausdorff measure of the set of self-intersection. Also, it was I don't didn't know this paper which you showed on the last slide, but you see also maybe they study some continuity properties of hyperelliptic diffusion or only visitation properties. What do you think can be related? Can your results be related to the continuity properties of trajectories of Brownian motion on Carnot group?
Well, it depends what you mean by continuity properties. There are different properties that we can write. We can write in this paper. There are some things that they use on the process, but I'm not sure that it is exactly what you mean.
The simplest one is the Levy model of continuity for Brownian motion. It looks like
you mean infinitesimally? So So maybe not exactly. They have some kind of expectation from the supremum of the distance, but not maybe not exactly. But here, I want to say that actually here we have to study not the continuity. We actually do this. So here, we study the not continuity of the process, but basically local time in some sense. So here we obtain something about local time. And it is here, I told you, if I take power p, so I can do more precise calculations with additional logarithm, maybe. So this is exactly what was done in this paper. The calculations were more precise, and they obtained a little more precise result in the sense that Hausdorff measure had additional logarithm. And yes, in Taylor, I saw that they also studied some kind of asymptotics, and then asymptotics can be related also to back to Hausdorff measure. So yeah, it is true. But in this particular proof, I don't think I need it. But maybe.
Yes, and I understand, but maybe just some other related question. What do you know about the about infinitesimal asymptotic properties of Brownian motion on Carnot group? Does it very different from Euclidean case or not?
No, I don't think it's different, but maybe some different parameters here, but no. It is. I think the point in this relation was that it was exactly the same as for any diffusion for some reason, but it is just a specific relation. So maybe if you consider some continuity in sense and some almost sure results, so maybe it is different. But almost sure results I did not see. Maybe if I look again in this paper, they did a lot of on this hyperelliptic diffusion, and not just in this paper. They had another paper too, so maybe, or maybe another. Legal had two more papers, I believe, in a similar topic. Maybe they did something, but for hyperelliptic diffusions, I did not see any other papers except papers of Legal. So maybe.
Yes, I understand that if we consider hyperelliptic diffusion in Euclid space and have this Aronson type estimation on the density, then of course I think we can prove something like law of iterated
Oh
logarithms.
yeah, you're right. Maybe we can just use estimates on the
On the density, yes.
heating times, maybe something else. Yes.
But now let us came to your case when you consider Carnot group. You consider different distance. And maybe due to this difference in distance, at least some formulation of the infinitesimal properties will have new kind.
Yes, so again, back to this paper. So in this paper, they use the corresponding distance, and then they obtain something that looks similar to other different. So this distance that corresponds to the process is a natural way to show the properties of the continuous. Maybe you are right, but yeah, right now I only remember this one with
Okay. So such subject is more or less already studied, yeah?
a little bit in this paper, but that's it.
Okay.
Yeah, so maybe it is not studied in the sense that you mean it. So it is possible. Maybe almost properties were not studied for such process. But I have to again look. Yeah, I'm not sure.
Okay, thank you very much. Some other questions, please? If there are no other questions, then thank you again for interesting talk, and we hope to see continuation of this theory. And maybe Georgi know who will be the next speaker.
Next speaker will be Vitaly Narovsky about massive modified radial flow.
Okay, let's see what happened with this flow next week. For today, we finish our job. Thanks everybody, and bye.
Thank you. Bye.
Bye.
Thank you. Bye.